To study sensitivity analysis, let's first look at the impact that it will bring when we change the objective function coefficients. And if you think in terms of the graphical solution that we use to solve an LP model, which part do the objective function coefficients relate to in that graphical solution? They define the slope of the level curves, right? So if you think about it, when we defined those feasible regions using the constraints, then the next step is to plot the level curves using the objective function coefficients. And the coefficient determines the slope of those level curves. When we have the level curves drawn on that feasible region, depends on the slope, how steep it is or how flat it is. It will touch one of the corner points of your feasible region, gives you the best optimal objective function value. For example, if it's a maximization problem, then you want that to touch that corner point that gives you the highest intercept on your vertical axis. And if it's a minimization problem, then you want the minimized, the smallest intercept on your vertical axis. And when the slope of the level curves change, the optimal solution can change from one corner point to another. For example, using this graphical solution, if we have the original level curve like this, so this line here, the original optimal solution would be at this point. That gives you the largest intercept on the vertical axis. But if we change the level curve to this slope here, okay, so this one, if the slope changes, the new level curve will be drawn like this. So this original optimal solution point with this new level curve, with a flatter slope, will no longer give you the highest intercept on this x2 axis. Thus, the optimal solution moves to this point where you get the highest intercept on the x2 axis. So I'll use this graphical representation to show you how when one of those coefficients change, that will change our optimal solution. And in sensitivity analysis, what we would like to find out is how much can these values change without changing the solution to another corner point. So there should be a range within which these two values can change without changing our optimal solution. Or we want to find out when or how much the change to these two values can be before our solution change to, for example, from this point to another point. So let's use this graphical solution to just to show you. I apologize, like these values, they are not shown correctly, but they are the same with what I just showed on the slide. Okay, so if you look at now, this dotted blue line here, this represents my level curve, while the three color lines, the orange, the red, and the purple lines represent my three constraints, and they define the feasible region. So my current level curve is defined by the slope, that's the 350 and the 300 here. But if you keep looking at, keep your eyes on this dotted blue line, and while I decrease it, okay, so I just decrease this profit for the equals bus. Keep looking at it. You can see, can you see the blue line moving? So if you keep decreasing it, the slope is not at the point where change this optimal solution. So even though the slope of this level curve make it flatter now, at this corner point, it still gives you the highest intercept value on this x2 axis. But we will just keep changing, and it almost overlaps with one of the constraints now. If I keep changing, then you see when this level curve overlap with this constraint here now, when they have the same slope, the overlap, we talk about this. All those points on this edge here, where my level curve and this constraints that define this edge of the visible region overlap, all the points on this section will become an optimal solution. So this is the special situation that we talk about called alternative solution. Okay, so alternative solution happens now, and the original point, this optimal solution point is still one of them. Okay, but if we keep decreasing that coefficient, you see, originally it was this point, and then it changed to alternative solution. All the points, including this one and this one, are our optimal solutions. Then I kept decreasing this value here, and our optimal solution changed to this point. And if I keep decreasing, you can see that the blue dotted line, that level curve line, kept going flat. But this point remain to be my optimal solution point, right? Until, if you make a prediction, if I change it to the same slope of this constraint here, then the optimal solution becomes to be all the points on this edge now. So we have, again, the special condition, alternate optimal solution. Then if we keep decreasing, what's your prediction? If I keep decreasing this value, which point will be, what happens to the optimal solution? Originally was this point, and then becomes all those points, including this one. And similar to what happened earlier, if I keep decreasing it, this point will be the new optimal solution point. Okay, so going back to our slides here. When we change the value of our objective function coefficient, it will change the slope of our level curve. When the slope of level curve change to a certain degree, then our optimal solution will change from one corner point to alternative solution and then to another point. So now, this is the sensitivity report generated by solver that we're going to study. We're going to focus at this part first. Once solver shows you that window saying that the optimal solution has been found, you will be able to choose sensitivity report, answer report to be generated. If you choose to have a sensitivity report to be generated, then you will see something like this. And if we look at the different part of the sensitivity report, the first table basically shows you what the target cell, or we said that's the objective function cell is. Okay, so it shows you the current value for your objective function is this much. And it's referring to that cell that contains that objective function and what the name is. So the name here, solver will take it from the column and the row heading you have. So having meaningful row and column headings can be very helpful in helping us understand the sensitivity report, because it will take the column and the row headings for those cells. You can see here, we have the B5 here, and it will take the heading, the number to make for the equals plus, number to make for hydrolysis. So these two are the column headings, and this number to make is the row heading that solver will take automatically for you. Okay, so now this second table here are the adjustment cells. And telling from here, this part, it tells you those two cells, what they are and what their final values are. And if you recall, these are the optimal solution values, so our x1, x2 value. So now we're going to jump to here. So we'll look at the reduced cost later. The objective function coefficient tells you the current values for your objective function coefficients. Then what's this part? It shows allowable increase and allowable decrease. So the 100 and the 50 for 350. Now if we come back to here, I'll reset it back. Okay, so our original values are 350 and 300. Now from that sensitivity report, it says allowable increase is 100. Allowable increase, let's increase it to 450. Okay, so we see when you increase to 450, all the points on this edge become the optimal solution. But you know that this original point is included. And when we change this from 450 to 451, what happens? The optimal solution changed to this point. Okay, similarly, let's change it back to 350. And from the sensitivity report, it says allowable decrease is 50. If you can make a prediction, what will happen when we change this value from 350 to 300? What do you think will happen? So the similar thing happens, this point included, but all the points on this edge become the optimal solution to our problem. And if we keep changing this value, so now it's like at the very edge, if we change it by 1 more unit, our current optimal solution will no longer hold. Now we have 300, and that was a 50 units decrease from our original 350. If we keep changing it to 299, you see this point becomes our new optimal solution point. We're going to set it back now, okay? And similarly, if we look at the value for our the 300, that's the hydrolysis profit. Allowable increase is 50, and allowable decrease is 66. So if we do that, allowable increase, so 300 increase to 350, that's 50 units of increase. Then we have alternative optimal solutions. But this current optimal solution point is still our optimal. This point still holds. But if we keep increasing it, say 351, then you see this becomes the new optimal solution point. So with the graphical representation, hopefully you can connect it with this sensitivity report part and know that this part represents the allowable increase and the allowable decrease of the objective function coefficients without changing the final values of our optimal solutions. Okay, so the values in the allowable increase and the allowable decrease columns for the changing cells indicate the amount by which an objective function coefficient can change without changing the optimal solution, assuming all other coefficients remain constant. And please note that here when we talk about without changing the optimal solution, we mean that the decision variable values, not the objective function value. I found sometimes students confuse the optimal solution with the optimal objective function values. They are two different concepts. Okay, so if we think in terms of, for example, an investment, the solution could be the suggested decision or decision variable values, like how much to put in each of those investment options. So how much money to put in each bond. Then objective function value would be the results from implementing the solution. You use the suggested solution, which include the decision variable values, and implement them. Then your objective function value would be the result, like how much money you will get by implementing the solution. Okay, so make sure you know that the solution part and the objective function value part, they are two different things. And when we change the objective function coefficients, for example, the interest rate for the overall portfolio, then even though the solution does not change, meaning the amount of money we put in each bond, the result will still change, right? Think about it. We still put the same amount of money in each investment. So the solution is the same. The solution remains to be the same. But because the interest rates, which represent the objective function coefficients, these increase, then for sure your result, which is objective function value, will change too. So make sure that, when we talk about allowable increase, allowable decrease for the objective function coefficients, that's for the solution. That's for the decision variable values to remain to be the same, but not for the objective function values to be the same. Because if the coefficient change, then your objective function value will change for sure. Now, in the absence of a degeneracy, which is a special condition in LP models, we'll talk about later, the values of 0 in the allowable increase or decrease column for the changing cells indicate that an alternative optimal solution exists. So think about it, okay? When you have 0 allowable increase or decrease, what does that mean? Means just the slightest change to that object function coefficient will change your optimal solution. So if you remember when we use the graphical representation, so if we use this graphical representation to think about that situation when we are at, for example, this point here. Okay, so remember that when we had this situation here, when our coefficient is 450, we had alternative solutions. This original optimal solution point is within one of those optimal solutions. But at this point, a slightest change to this value here will change our result. So it will become either this point or this point here. When we have alternative solutions, all those solutions are included. But if we change it, increase it by 1 unit, then our solution will become just this sole point. Or if we decrease it, say 449, our solution will become this point. So if you relate to this, when we have a 0 in those values, that indicates our final value for the decision variables will change for sure, given a slightest change to those coefficients. And that happens when we have alternative solutions, that all the points on that edge are optimal solutions. And if you change the coefficients of your objective function or the slope of your level curve a tiny bit, the decision variables will change to either point at that two ends of that overlapping edge. Okay, so a 0 in the allowable increase or decrease column for the changing cells indicate that the special situation, which is alternative optimal solution, exists. And note that the software does not really alert you to the existence of alternate optimal solutions. You will need to look at the sensitivity report to identify this. When you look at the sensitivity analysis report, you see that alternative solutions exist. And if you are interested in finding out a different solution, here's one way you can do it. So you would look at if it's the allowable increase or if it's the allowable decrease that is 0. Then you add a constraint for that model, making the objective function equal to current optimal solution. Okay, so you would add constraint to set that objective function cell to be equal to the current optimal value it gives you. And then make your objective function to either maximize that decision variable or minimize that decision variable, depends on if it's the allowable increase or the allowable decrease of its coefficient that is 0. So if you're interested, then give it a try. Next, we'll talk about the simultaneous changes in the objective function coefficients. So what we talked about earlier represent that if you just change one of the coefficients, Say if you increase or decrease the unit profit of the equals bus, those allowable increase and decrease tells you that how much you can change this coefficient value without changing your optimal solution, assuming that the unit profit for the hydrolysis remain to be the same. Okay, but sometimes we may be interested in knowing what about both unit profits change? What happens? Can we get some information from the sensitivity reports on simultaneous changes in the objective function coefficients? The answer is sometimes. Okay, so we can use the 100% rule to determine if the optimal solutions will change if more than one objective function coefficient changes. And two cases can happen. In the first case, all variables with the changed object function coefficients will have non-zero reduced cost. And the other case is at least one variable with the changed object function coefficient has a reduced cost of 0. So let's look at the first one. So in the first case, when you observe that sensitivity report and you see that all those variables that you want to change their coefficients have non-zero reduced cost, then the current solution will remain optimal if the objective function coefficient changes are all within their allowable increase or decrease. So what does that mean? If you look at the reduced cost section of that sensitivity report and you found that they are all non-zero, then as long as you change those coefficients within their allowable increase and decrease, then whether you change one or more than one, if you change all of them simultaneously, your current solution will remain to be optimal. Now, the second case is seen more often. At least one variable for which you want to change the objective function coefficients has reduced cost of 0. Then we will need to use this 100% rule. For each variable, we're going to compute the percentage of changes to that allowable increase or decrease. Okay, so this delta C here represents the amount of change. And if you want to increase it, then your denominator would be the allowable increase for that coefficient. And if you want to decrease it, so this amount of C that you're going to change is decreasing, then you would use the allowable decrease of that coefficient to calculate this percentage. And you calculate that for each of the variable and you add them together. If more than one object function coefficient changes, the current solution will remain optimal if the sum of all those R's, the percentages, is less than or equal to 1. Okay, but if you sum up all the percentage changes and the value is greater than 1, then we are not sure. Okay, so the current solution may still remain to be optimal, but it's not guaranteed. The only thing we know is that if the sum of the change as a percentage of the allowable increase or decrease is less than or equal to 1, then we can conclude that our current solution will remain to be optimal. And you see, this method applies to both cases. So if you don't remember specifically what the rule is, then just use this 100% rule to calculate. So this concludes the part on the sensitivity analysis to the objective function coefficient changes.